Hello and welcome to Circuit Lab, practice number 13, RC Circuits. I'm Mr. Burleson and you can always reach me at geaux15@hotmail.com. In the last practice, we talked about diodes. We talked about how it's a two-terminal electronic device that allows current in one direction and how it can be shown as a switch that is either open or closed depending on whether it's forward biased and open, or closed or on, or if it's in reverse bias, in which case it is off or shown as an open circuit. We talked about how an ideal diode is basically either an open or a short circuit with no voltage. However, we also talked about light emitting diodes, which actually are a special type of diode which emit light. Okay, so they act just like a diode, and depending on the material, they emit different colors of light. We also went over operational amplifiers, where we talked about the uses for an operational amplifier and the design parameters for creating a comparator, an inverting amplifier, and a non-inverting amplifier. We talked about how an ideal op-amp has infinite gain, has infinite input resistance and zero output resistance, and again has potential for infinite gain. But today we're going to talk about capacitors. And a capacitor is a passive two-terminal electrical device that stores the potential energy in an electric field. Okay, and we talked about this earlier in one of our previous practices, where we were talking about how the charge builds up on both sides of the capacitor, and then once it's fully charged, no current proceeds. The total charge is equal to the capacitance times the voltage. We talked about how on a capacitor, all the charge, all the positive charges will get on one side and all the negative charges will get on a different side. The simplest model of a capacitor is two parallel plates that have an area, let's say A, with a very, very small amount of distance between the two plates, D. The material will have a different dielectric property, and dielectric is a non-conductive material, and so the dielectric permittivity, epsilon, of the material determines how much capacitance can be held, such that the capacitance is equal to epsilon times the area divided by the distance. So, and the energy stored in the capacitor is equal to 1/2 CV squared. Keep in mind that if we're looking at the permittivity of air, it's about 8.854 times 10 to the minus 12 farad per meters. So, one of the more common uses of capacitors is to create an RC circuit. So most RC circuits will involve some form of a resistor and some type of a capacitor. The capacitor is either charging, in other words, it's getting up to its maximum voltage where current would stop flowing, or it's discharging, in other words, you started at a particular voltage and then it discharges as the charges are then released and the electric field eventually goes to zero. So usually you'll start with a switch that will either allow it to be charged or it'll switch to a different position and be discharged. There will be a time constant, rho, that is equal to, tau, that is equal to RC. Okay, so you take the R's in ohms and C is in farads. Okay, and it turns out that the time it takes to charge the capacitor it takes about tau time to charge a capacitor to about 63% of its maximum value. Tau is also the time that it takes for a capacitor to lose about 37% of its original value. Keep in mind that charge and voltage won't change instantaneously. So they'll always have like a time, usually t equals 0, when the switch is changed. Okay? So when you first start charging a capacitor, it actually acts as a short in the short term. In the short term, it acts as a short, and then as the charge is built up, it eventually becomes an open circuit for the current. Okay, so it starts as it starts very high and then goes to zero. Okay, however, when it's discharging, it will start at the maximum value. So in other words, while it's discharging, whatever that maximum voltage is, V divided by R, that's the current it starts at. And then it slowly goes down as it discharges, going to zero in the long term. Okay? And what they'll usually try to do to make sure that you understand whether it's fully charged or fully discharged, they'll tell you that the switch is set to a particular setting for a long period of time. So if I look in this particular case, if switch is set to B for a very long time, that would completely discharge the capacitor, and the voltage of the capacitor would go to zero, and the current through the capacitor would also go to zero. Now if it was set to A for a very long time, the capacitor would be fully charged. Okay, and so since it's fully charged, no current can go through it, so the voltage of B would equal to the voltage of C because there's no current going through R. So the maximum voltage that this capacitor in this particular case would assume when the switch is set to A for a very long time is VB. Then what happens is that most of the RC problems are going to involve either charged by battery and then discharged, or well, actually most of them involve being charged by battery and then discharged. So remember that most of the more interesting ones involve either during the time that you're charging it or the time that you're discharging it. So if you're starting it discharged, VC T equals 0, so VC at that point, since there's no charge, it's equal to 0. The switch is turned on, okay, at T equals 0, the capacitor begins to charge. And so the charge as a function will be equal to whatever the maximum voltage is, which in this case would be VB, times 1 minus E to the minus T divided by RC. So you'll notice T is in seconds and RC or tau is also in seconds. Okay. Now what you'll notice is that you will hit the maximum charge eventually of the system at some point in the future. So the common problem solution method: first, find the start condition. It's either going to be, almost always it's going to be fully discharged or charged. Then determine the impact of the charge at T0. Are we going to be charging or discharging? Now, remember, combine capacitors as if needed as normally. So capacitors are a little bit different in that the way you combine them is the exact opposite as the way you combine resistors. So if they're in parallel, because their areas add, they add. So this is very similar to how if you were combining resistors in series. And if they're in series, then since the charge is split amongst them, it's very similar to how resistors are calculated in parallel. Solve for the equivalent R as seen by the capacitor during the charging. Okay, so in other words, you're always looking at the system based upon what the R is. Okay, in those cases, treat the voltage sources as shorts and all the current sources as open. Combine normally and then determine what the maximum charge voltage would be in the charging position. Now that you have the R and you have the C, you can calculate tau equal to RC. Using the Vmax and the tau equal to RC, you can resolve the current and voltage or charge. Okay. So for practice, what I'd like you to do is figure out what the time constant is for charging the system to the right if R1 equals R2 equals 1 kilo ohm and C is equal to 10 millifarads. Okay, so in that particular case, okay, if we're charging the system, okay, and what you'll notice here is that as it's being charged, okay, the maximum voltage when C is open is basically the split of R1 and R2. It turns into a voltage splitting situation, and since R1 equals R2, okay, then the fully charged value of C, if it's 12 volts, would be 6 volts. Okay, the time constant, and you remember we look from the capacitor and we short out the V. When we're doing that, it's R1 in parallel with R2, so the time constant, the R equivalent, will be 500 ohms, and C is equal to 10 millifarads. So you take 500 times point 10 millifarads is 10 times to the minus 5, and so it'll be like 5 milliseconds. Okay, if fully charged, the battery is removed. How long to discharge 37% of the charge? It would be equal to the time constant. If after fully charged the battery is removed, okay, leaving a short, how long to discharge 37% of the charge? If fully discharged and the battery is added at T0, what is the formula for IR2? So these are some good examples. So now let's look at this particular case. What is the maximum voltage for VC if the switch has been closed for a very, very long time? So if it's closed for a very long time, I'm charging up the system. Okay. Now, what that means is that if it's been closed for a very long time, I can assume that the capacitor is fully charged, and so it's completely open. And so in this particular case, okay, my voltage is basically split between the two parallel streams. And I've got 15 on one side and I got 10 on the other. And they've both got the same amount of voltage. They both got 12 volts. Okay. And what you'll notice is that on one side of the capacitor, I've got a different voltage than on the other side of the capacitor. So on one side, okay, the 10 to 5, that's 2 to 1, so that's 8 volts along the 10 ohm capacitor and 4 volts along the 5 ohm capacitor, and so that means that it is equal to about 4 volts right there. Okay, on the other side it's 1 to 9, so now I divide it by 10. Okay, so that's 1.2, and what you'll notice is I'll have 1.2 ohms, and then below that I'll have a much larger amount. I'll have 10.8. So the maximum voltage, if you will be 4 minus 1.8. So hopefully, or excuse me, 4 minus 10.8. And so that would be the maximum voltage. Then I open the switch at t equals 0. And in that particular case, now the entire left-hand side of the equation can be ignored. Okay, and I start at the maximum voltage, and I take 11 ohms in parallel with 14 ohms, and that is my R, and I multiply it times C, which is 2.2 microfarads, and then that's how I get my time constant. So again, update your binder, do your circuit problems from the homework generator, do level 16 operational amplifiers and level 17 RC circuits. Make sure you can do all of the in-class problems. I'd like you to design an RC circuit with a 10 picofarad capacitor that has a maximum voltage of 10 volts and time constant of 0.3 milliseconds. Show all your work. And determine the equation for current, charge, and voltage as a function of time for the capacitor in that design. Thank you so much.